The sound absorption coefficient is an important parameter for microperforated panels, which are widely used for interior noise control in buildings. Hello, I'm Armin. In this video, I'll show you how to calculate the sound absorption coefficient of a microperforated panel using Mohs theory. If you're not familiar with Mohs theory, don't worry, I'll briefly explain the theory in the following slides before we start the simulation.
Microperforated panels, or MPPs, are a type of Helmholtz resonator consisting of a thin panel with very small holes and a backing cavity. They are commonly used in the walls and ceilings of buildings to reduce interior noise. They provide sound absorption through high viscous losses as air passes through the small holes. Therefore, MPPs do not require porous materials to absorb sound.
A fully detailed geometry with a large number of small holes would require millions of elements in a finite element model. Da-Yu Ma addressed this issue by developing an approximate impedance model for a single circular hole, with an error of about 6%, as shown in the following equation. This impedance can be applied as a boundary condition in an FEM simulation. Therefore, there is no need to model the individual holes or the MPP thickness. Instead, we can apply the impedance to an equivalent surface using only the hole diameter, panel thickness, and perforation ratio. For this tutorial, I used the data from Figure 5 of Da-Yu Ma's paper and validated my results against the experimental data. The impedance tube is 10 centimeters in diameter, with a panel thickness of 0.2 millimeters, a hole diameter of 0.2 millimeters, a cavity depth of 6 centimeters, and a perforation area ratio of 0.05%. Finally, the results show good agreement with the experimental results. Note that the simulation is valid only up to the impedance tube's cutoff frequency, approximately 2000 Hz. Before starting the tutorial, I would like to introduce the reference paper, Potential of Microperforated Panel Absorber, published by Da-Yu Ma in 1998. That's enough introduction. Let's get started. I will click on Model Wizard. Since the impedance tube is a 3D model, I will select 3D. Under Select Physics, I need to expand Acoustics, then expand Pressure Acoustics, and select Pressure Acoustics Frequency Domain, because we want to perform the simulation in the frequency domain. I will click Add, and as you can see, the Pressure Acoustics Physics interface has been added. In the Review Physics Interfaces section, we can see Pressure Acoustics with the dependent variable P. This is the dependent variable, and all the other variables, such as sound pressure level and particle velocity, will be calculated based on the acoustic pressure.
Next, I will click Study. Under Select Study, we need to select the study type, so I will select Frequency Domain and click Done. Before creating the geometry, I would like to change the length unit from meters to millimeters because the dimensions of the geometry are relatively small. It is better to use parameters when creating this model, although you can also enter the values directly when defining the geometry. It is not necessary, but I prefer to use parameters.
I will click Parameters. Then, click the Load icon and select the parameter text file. After that, I will click Open.
As you can see, I have defined 4 parameters for this simulation.
The first one is cavity depth, which is a geometry parameter. The other 3 are panel thickness, perforation diameter, and perforation area ratio. These 3 parameters will be needed later for modeling the microperforated panel. Now, let's create the geometry. I will right-click Geometry 1 and select Cylinder from the context menu. Alternatively, we can go to the Geometry tab and select Cylinder from the primitives. The radius of the impedance tube is not specified in the paper, but a typical impedance tube has a diameter of around 10 centimeters. corresponding to a radius of 50 millimeters. The height of the impedance tube is not important because it does not affect the sound absorption coefficient, so I will use a height of 400 millimeters. This value is not critical, so you can use a smaller or larger value if needed. I also want to create the cylinder along the x-axis, so I will change the axis type from z-axis to x-axis and click Build All Objects. Here you are. We now have our impedance tube. The next step is to create the microperforated panel. Since the microperforated panel is a boundary, I need to create a work plane to define its location. I will click Work Plane from the Geometry tab, and the work plane has been added. Under Plane Definition, I will change the plane type from Quick to Face Parallel and select the terminal face of the cylinder.
For the distance, I will enter D and click Build All Objects. I also need to check Reverse Normal Direction. Here you are. Now, there are two ways to create the cross-section. One way is to partition the tube using this workplane. To do this, we can go to Booleans and Partitions, select Partition Objects, and then select the cylinder. Under Partition Width, I need to change the selection from Object to Workplane, and then click Build All Objects. Here you are. The cross-section has now been created, and we can assign the microperforated panel to this cross-section later. The next step is to define the material. I will right-click Materials and select Add Material from Library from the context menu. In the Built-in node, we can select the most important material. I will expand it, and as you can see, air is listed here. I will select it, click Add to Component, and then close the Add Material menu. As you can see, there are two domains because I partitioned the impedance tube with a work plane. In the Material Contents section, two properties are used: density and speed of sound. Now let's add the boundary conditions for the impedance tube. We need a port for the inlet and an interior perforated plate for the microperforated panel. I will right-click Pressure Acoustics and select Port. The port boundary condition is commonly used to calculate acoustic properties such as sound transmission loss and sound absorption coefficient. I will select the inlet of the cylinder. Under Port Type, we need to change the setting from User-Defined to Circular because the cross-section of the tube is circular. Next, I will scroll down the Settings panel and set the amplitude to 1 Pascal. The amplitude does not affect the sound absorption coefficient because we are using a linear acoustic model. We also need to right-click Port 1 and from the context menu, select Circular Port Reference Axis. This feature requires 2 points to define the acoustic modes of the duct. I will remove all the existing points and select 2 points on the cross-section. The next step is to define the microperforated panel. I will go to the Physics tab, expand Boundaries, and select Interior Perforated Plate. This boundary condition uses Ma's model to calculate the acoustic properties of the microperforated panel. I will select the cross-section as the perforated plate and enable transparency to get a better view. If we scroll down the settings, we can see 3 parameters under Interior Perforated Plate: hole diameter, plate thickness, and area porosity. The area porosity is sigma, which I defined earlier in the parameters. The plate thickness is T, and the hole diameter is D. Everything looks good, but we still need to specify the material. I need to change the boundary material to air. Now everything looks good. The next step is to define the frequency range, because the mesh is frequency dependent. As the frequency increases, the mesh needs to become finer. I will click on Frequency Domain, and then click on Range. Here, we can specify the start frequency, stop frequency, and frequency step. However, I would like to use octave bands. Under Entry Mode,
I will change the step to ISO preferred frequency, and under interval, I can select 1/12 or 1/24 octave. I will select 1/24 octave and set the frequency range from 10 Hz to 4000 Hz. Then click Add. As you can see, the frequency interval is now defined according to the octave scale. Now, if I click on Mesh 1 and select Build All, the maximum element size will be determined based on the maximum frequency, which is 4000 Hz. Everything looks good, so we can now click on Study 1, select Compute, and wait for the solution. The solution is complete, and it took about 2 minutes. Let's look at the sound absorption coefficient. The sound absorption coefficient is not included in the default results, so we need to create it manually. We need a 1D plot group because we want to create a 1D plot. I will right-click Results and select 1D plot group. I can change the label to Sound Absorption Coefficient, although this is optional. We also need an XY plot, so I will right-click the 1D plot group and select Global. In the expression field, we need to enter the formula for the sound absorption coefficient. The sound absorption coefficient is calculated from the reflection coefficient, and the port gives us the reflection coefficient. I will click the Add Expression button, expand Pressure Acoustics, then expand Port, and select S11, which represents the reflection coefficient. If I click Plot, we can see the result. Now, let's enter the expression for the sound absorption coefficient. The absorption coefficient is equal to 1 minus the absolute value of the reflection coefficient squared. I will click Plot. Here you are. This is the sound absorption coefficient plot. We can use a smaller frequency interval, such as 5 Hz or 10 Hz, to obtain a smoother and more detailed plot. Now, let's make the plot look a little better. I will click on Sound Absorption Coefficient and enable the X-axis and Y-axis labels. For the Y-axis label, I will type alpha, followed by Sound Absorption Coefficient. For the X-axis label, I will enter frequency in Hertz. Under Title, I will change the title type to Label, so the label Sound Absorption Coefficient will appear as the title of the plot. Now, let's adjust the line style. I will click on the global one, expand Coloring and Style, and set the line width to 2. Now the plot looks much better. Let's compare the plot with the one in the paper. Figure 5 in the paper covers a frequency range from 50 Hz to 8000 Hz, so we can change our plot interval to match it. I will go back to the sound absorption coefficient plot and open the axis settings. Here, I can set the x-axis minimum to 50 Hz and the maximum to 8000 Hz. For the y-axis, I will set the minimum to 0 and the maximum to 1. I also need to enable the x-log scale, which makes the plot look similar to the one in the paper. Now, let's extend the simulation to 8000 Hz. I will go back to Step 1, Frequency Domain, click on Range, change the maximum frequency from 4000 Hz to 8000 Hz, and click Replace. Now, if I go back to Mesh 1 and click Build All, the mesh becomes finer because the maximum frequency has increased. Let's click on Study 1 and select Compute to run the simulation. The solution is complete. This time it took about 25 minutes. Now I will click on Sound Absorption Coefficient to see the results. I also need to update the axis limits. I will set the x-axis minimum to 50 Hz and the maximum to 8000 Hz, and set the y-axis minimum to 0 and the maximum to 1. Then I will click Plot. Here you are. This is the sound absorption coefficient plot, which we can now compare with the results presented in the paper. The cutoff frequency of impedance tube is about 2 kHz, and the results are valid up to this frequency. That's why the experimental test shows up to 2000 Hz in Figure 5. I will finish the tutorial here. Thank you for watching.